morning, friends. In chapter 13, kinetic theory of gases, last we discussed about the postulate of an ideal gas. Right? Just to revise the postulate, first is the gas is made up of the microscopic particle, and these particles are the molecules. Right? Now next is these molecules can be considered as the rigid sphere with the internal structure. That means these molecules are the rigid sphere. That means its shape does not change. Now third is the molecule of a gas perform the random motion. Fourth postulate is that during the random motion, molecule following or the obeying the laws of motion suggested by the Newton, that means the Newton's laws of motion. Right? Now next, the number of molecules in a container or in a gas is very large. The number of molecules in a gas is very large. Now sixth is the volume occupied by the molecule of a gas is very small or the negligibly small compared to the volume of a gas. That means these molecules are very small in size, therefore the volume of the one molecule of a gas is very small compared to the volume of a gas. Now 7. The collision of molecule and also with the wall of a container is perfectly elastic, and the time interval of the collision is very small compared to the time interval between the two successive collisions. So we are keeping this postulate in mind, and we are going to derive the next question. Due to the collision of the molecule of a gas with the wall of a container, whatever the momentum is imparted on the wall of a container. Already we discussed about that. The molecule of the gas perform the random motion. During this random motion, this molecule collide with the other molecule or wall of a container. So how much momentum is transferred to the wall of a container due to the collision of a molecule in given time or the delta t time of interval. So we are interested to derive this equation. For that purpose, the question is asked like that way: obtain an equation of momentum transferred to wall of a gas container in delta t time. Right? For that purpose, we consider that it's shown in the figure. Consider a gas in a cubic container. Right? The side of each side, length of each side of a container is L. Therefore, area of each side of a container is equal to L square. And all the wall or the each side are the perfect elastic. Perfect elastic. So we write like this way. It's shown in the figure. Just video the figure. Consider the gas is filled in a cubic container. The length of each side is L. Therefore, the area of each side of a container is A is equal to L square, and all sides are elastic, because the collision of the molecule with the molecule and molecule with the wall of a container are perfectly elastic. And due to that result, we also assume that the each wall are the perfectly elastic. Clear? The one corner one of the corner of a cube is taken as an origin of a Cartesian coordinate system. For that purpose, first we do the container, and one of the corner is considered as an origin. For that purpose, there is the cubic container. Here we consider this corner as an origin of a Cartesian coordinate system. Therefore, there is the x-axis, there is the y-axis, and there is the z-axis. Right? There is the x-axis, there is the y, and there is the z. Now, there is the wall A1. And opposite wall is this. There is the wall A2. Now here we consider this corner as an origin of the Cartesian coordinate system. There is the cubic container and the length of each side is L. Therefore the area is L square. All the walls are perfectly elastic. Now consider a molecule having the mass is M. Here we consider the one molecule having the mass is M. Its velocity is v. Therefore the component of velocity are vx, vy, vz. These molecules are moving along the direction of x-axis, and during this motion it collides with a wall A1. And then due to the perfect elastic collision, that is they bounce in this direction. So after the collision, the velocity of this molecule becomes minus Vx, while Vy and Vz remain unchanged. Now consider a molecule of mass n and velocity v. The component of velocity are Vx, Vy, Vz. Right? Okay. So here we consider the molecule of mass m and velocity v. The component of velocity are Vx, Vy, and Vz. Now, when the molecule collides with the wall V1, right? So the component of velocity Vx is only changed. Component of the velocity due to the collision with the phase A1, the component Vx is only changed, then becomes the minus Vx, while the Vy and Vz is remain unchanged. When a molecule collides with wall A1, the Vx component becomes minus Vx after collision, while Vy and Vz remain unchanged. Therefore, the momentum of a molecule before collision is equal to mvx. Initially it is moving along the x direction with the speed vx and mass is m. Therefore the initial momentum is mvx. And after the collision, is equal to minus mvx, because the mass is remain as it is, but the direction of velocity is changed, and that becomes the minus vx. Therefore, after the collision, the momentum of a molecule is minus mvx. Thus, the change in momentum of a molecule is equal to final momentum minus initial momentum. So it's equal to minus 2mvx. Minus 2mvx. So that is the change in momentum of a molecule. So from Newton's third law, the momentum imparted on a wall due to the collision of a molecule is equal to 2mvx. This is the equation number 1. So when the one molecule is collided with the one A1, so the change takes place in the momentum of a molecule is minus 2mvx, but from Newton's third law of motion, the same momentum gained by the wall but in opposite direction, therefore there is the 2mvx. Clear this? So first paragraph, initial is the description of the figure. It's shown in the figure. Consider a gas filled in a cubic container. The length of each side is L. Right? The area of each side of the container is A is equal to L square, and all sides are elastic. Now, the one of the corner of the cube is considered as an origin of a Cartesian coordinate system. One corner of this cubic container we consider as an origin. Right? Now, we consider the one molecule of mass m and velocity is v. The component of velocity are Vx, Vy, Vz. Okay. When a molecule collides with a ball A1, the Vx component becomes the minus Vx after the collision, while the Vy and Vz remain unchanged. The momentum of a molecule before the collision is mvx, and after the collision is minus mvx. Thus, the change in momentum of a molecule is final momentum minus initial, therefore minus 2mvx. Now, the momentum imparted on a ball due to the collision of a molecule is 2mvx. Now, we are interested to obtain the equation of the momentum. How much momentum imparted on the ball in delta t time due to the whole molecule? This performing the random motion within the cubic container. For that purpose, we consider that the molecule moves with the speed or the velocity vx. Right? Within the distance delta T or the delta D is equal to Vx into delta T. Molecule hit the wall in delta T time. That means when the gas molecule moves with Vx, then in delta T time the molecule hit the wall only if they are within the distance delta D is equal to Vx into delta T. Vx into delta T. Now what it says there? Here, what are the molecule? There is the wall A1. Here the one molecule is traveling towards the wall A1 with the speed Vx. Right? Actually in a container not single molecule are present, numbers of the molecules are present. We are interested first to find out how many numbers of the molecule collide with the wall A1 in delta T time. Now here we consider the speed of a molecule. All the molecules are moving with the same speed Vx. Therefore, the molecule, number of the molecule collide with a wall A1 in delta T time with speed or the velocity Vx. Only those molecules are in the distance delta D is equal to Vx into delta T. Because we know that Vx is equal to delta D upon delta T. Distance upon time, that is the velocity. So what are the molecules within this distance delta D is equal to Vx into delta T time? It can collide with the wall. Or what are the molecules is more than this distance cannot collide or the can't collide with wall A1 in delta T time. Suppose our speed is 200 meter per second. So in 1 second how much distance we cover? 200 meter. This distance D is equal to 200 meter. So we can travel in within the 1 second this distance. Suppose we are at 250 meter distance. So we can travel this distance in 1 second? No. So here the same thing. So what are the molecules lying in this region or this distance Vx into delta T can make the collision with the wall in delta T time. Right? But here there is a cubic volume having the area is A. Therefore, the number of molecule or the molecule within the volume A into Vx into delta T collide with the wall in delta T time. So that is in distance and the molecules in volume A Vx into delta T collide with a wall in delta T time. Because here the container is 3-dimensional, that means the cubic. So not only the line, the molecular line, but here in this volume, what are the molecule are lying make a collision with wall A1 in delta T time. Clear? Now, if the numbers of the molecule in unit volume is small n. Therefore, total number of molecule collide with a ball in delta t time is equal to n a reacts delta t. So this number of the molecule can collide with a ball in delta t time. Okay. Already according to the postulate, the molecule perform the random motion. Not all the molecule, this number of all the molecule traveling towards the A1. Due to the random motion, the some molecule are traveling in this direction. For that purpose, on an average, the half number of the molecule are traveling or the collide with a ball in delta t time. So from the probability we consider that suppose the half molecule are moving towards the ball A1 and makes the collision with ball A1 in delta t time, while the half are moving in other direction, so they are not make the collision with the ball. Right? For that purpose we can act like this way. Due to random motion of the molecule, random motion of molecules on an average half molecules makes collision with a ball in delta t time. Therefore, the number of molecule collide with a ball is equal to 1 by 2 and A reacts delta t. That is the equation number 2. So this number of the molecule make a collision with a ball A1 in delta t time. Due to the one molecule, the momentum imparted on the ball is this. We are interested to find out the total momentum imparted on the ball. Now, the momentum imparted, the total momentum imparted or the transfer on a ball in delta t time is momentum P is equal to, due to the one molecule 2m reacts into number of molecules half and A reacts delta t. To cancel, therefore nm A reacts into reacts square delta t. That is the total momentum imparted on the ball in delta t time. Therefore, the momentum imparted on a ball in unit time momentum imparted on a ball in unit time is, that is the P dash is equal to P upon delta t is equal to N M A Vx square. That is equation number 4. So this way you can obtain the equation of the momentum imparted on a ball by considering the postulate of an ideal case. Again we revise it. First the description of figure, what is shown in the figure. Consider, as shown in the figure, consider a gas filled in a cubic container. Right? The length of each side of the container is L. Therefore, area of each face of each side of the container is A is equal to L square, and all sides are perfectly elastic. Now, the one of the corner of a container is considered as an origin of a Cartesian coordinate system. So that is the description of figure. After that, consider a particle or the molecule of mass m and velocity v. The component of the velocity are vx, vy, vz. Now, when a molecule collides with a ball a1 with velocity v, only the vx component becomes the minus vx, while the vy and vz is remain unchanged. Therefore, the momentum of a molecule before collision, that is the initial momentum when it travels towards the ball, that is the mvx. After the collision, its momentum is minus mvx. Therefore, the change in momentum of a molecule is final momentum minus initial. Final is minus mvx minus initial momentum mvx. Therefore, minus 2 mvx. From Newton's third law of motion, the momentum imparted on the wall due to the collision of a single molecule is 2 mvx, same in magnitude but in opposite direction. That is the equation 1. Now we are interested to find out the total momentum imparted on a wall in unit time due to the whole molecule. For that purpose, when the gas molecule moves with Vx speed, then in delta t time, the molecule hit the wall only if they are within the distance delta d is equal to Vx into delta t. So what are the molecules traveling towards the wall A1 with the speed Vx? Only those molecules make the collision with wall A1 if they are within the distance Vx into delta t. And the molecule in volume A into Vx into delta t collide with a wall in delta t time. If the numbers of the molecule in unit volume is n, therefore the total number of molecule within this volume A into Vx into delta t is n a Vx delta t. Now, here in postulate we consider that the molecule of a gas performs the random motion. And due to that result, due to random motion of molecules, on an average half molecule makes the collision with a ball in delta t time, while the half molecule are moving in the other direction. Therefore, the numbers of the molecules collide with the ball in delta t time is equal to half NA Vx delta t. Now we know that the momentum imparted on the wall due to the collision of single molecule is 2 mvx. Therefore, total momentum imparted on a wall in delta t time is 2 mvx into half Na Vx delta t. 2 to cancel Nm A Vx square delta t. So that is the total momentum imparted on a wall in delta t time. Now in unit time, how much momentum is imparted? So divided by delta t, therefore P dash is equal to Nma Vx square. That is the momentum imparted on a wall of a container in unit time. Clear? Now in next, we consider this equation and we derive the equation of pressure act on a wall of a container in unit time.